protocol. Okay, so when you set up an IPsec connection between two machines, every single packet exchange between them is going to be encrypted. Okay, this is not like SSL where you've got a tunnel and then everything that goes through the tunnel is encrypted, but then lots of other stuff doesn't, right? In this case, everything between those two hosts is encrypted. So if one of them is a DNS server, the DNS traffic doesn't matter what it is, right? On the other hand, it's exclusive to those two hosts. So you're not setting general IPsec up for the whole world. That's not really how it works, okay? It's a bit more of a manual configuration that you do have to arrange between the two parties. So certificates can come into it, okay, in an enterprise environment so that any particular nodes in the network could set up an IPsec tunnel. But if you're dealing with some random entity on the internet, then IPsec is probably not, it's not really an appropriate tool at that point because you do have to exchange keys and all that kind of stuff. You have to authenticate the other party. So it does provide security for the data sent between the two computers or the two networks, depending on whether you're doing endpoints or tunneling mode. Okay. Most of the time, we're really encountering tunnel mode. There's not a lot of one-to-one endpoints that are being set up these days. It does happen in a controlled environment, but a lot of the stuff that we do is not well controlled. Like we don't control the entire environment. Right? So this was developed quite a long time ago. It was developed by the Internet IETF, the Internet Engineering Task Force, the IPsec subgroup. So they came out with this some time ago. Even the older clients had limited support for it. IPv4, it is not required to be supported within that standard, but IPv6, it is a requirement for anybody who develops a networking stack that they have to support IPsec by default. Okay. Now, the two big modes here are transport mode and tunnel mode. Most of what we're going to be talking about is going to be tunnel mode. Okay, but transport mode is a legit thing. So in this case, this is kind of the original formulation of it. And it's meant to set up that end-to-end conversation between two hosts. So everything gets encrypted between them. The protection can be authentication only or encryption only, or it can do both. So you could actually just verify the hosts are who they claim to be and then not worry about the encryption. You could even turn off authentication, though why you would do that, I'm not too sure. Okay. So this is used in most IPsec-based VPNs that use L2TP, layer 2 tunneling protocol, which is actually just an old, it's like an old dial-up protocol from way back. They've just repurposed it, okay? Now, we are going to set that up because Windows makes it pretty easy to set up. It's one of the easier ones for us to do, okay? Tunnel mode is a little bit more complicated, but it is your more typical VPN functionality, okay? In this case, all of your packets really are going through a tunnel kind of like SSL, okay? So what you're actually doing is you're wrapping your packets in other packets. The packets that are being encapsulated are being thoroughly encrypted, but the outer wrapper is not, okay? This is kind of important when you're dealing with network address translation because you can't encrypt everything, and the protections that are in place detect the modifications that NAT does and freaks out about them, right? And so if you actually tunnel those packets in other packets, then NAT's not going to freak out at you, okay? Okay, now we talk about those two modes, but those aren't actually formal modes in the protocol specification. So there's no like field in an IPsec packet which says this is the mode that I'm using. It's just how you choose to use packets in general, okay? So really what you do to create these different modes is you have your header IP packet, and then you have subsequent headers, which can exist in IP, okay? So the next header field, whatever you do there, that determines whether you're in tunnel mode or whether you're in transport mode. Okay, and so a router that's trying to do some routing, or any kind of client that's trying to process the information, it's going to look at the next header, and then it's going to understand what it has to do next. Okay. So if the next header value is another IP packet, then you've got an IP packet and an IP packet, right? In which case you're dealing with a tunnel mode. Okay, so IP squared, that means that you're tunnel. If it's anything else, TCP, UDP, ICMP, all of those, that means that you're doing transport mode, which is kind of the more old school way of doing it, right? Now, hashing comes into this a lot. So there's a lot of verification of data. We're not just talking checksums, we're talking hashes. That slows down the whole process. So IPsec is not going to speed up your internet connection by any stretch of the imagination. But what it does do is it makes sure that the data is well protected and hasn't been modified by anybody, either by hook or by crook, like either by accident or by some kind of sinister intentional modification. Okay. Now, Microsoft does have its own little proprietary IPsec policies and connection security rules, which doesn't play nice with other clients sometimes. Okay, your mileage will vary, but Windows to Windows, it works just fine, right? So just something to keep in mind. Now let's see. IPsec policy is not designed to allow one-way protection of traffic. Basically, both parties have to engage in this. You can't just, it's not like SSL where you can just verify, your banking server, and they don't have to verify you. This is a two-way process. And if you're protecting traffic between IP addresses between hosts A and B, then you have to specify both traffic from A to B and traffic from B to A within your policies in Windows. Okay. You can create one-way filters to block access to certain services. So if someone's VPNing into your network, so let's say you want, you want people to do remote work, and they're going to do it through VPN. You can allow things like, well, we're going to allow you to connect to DNS, and we're going to allow you to connect to this remote desktop server, but we're not going to allow you to connect to this other server, let's say a web server. Okay. So you can, it's part of the Windows firewall, it kind of integrates with it. You can block at that level where you're just saying, you know what, those services aren't available to you, which is good because you don't want to have people's access to your network kind of all or nothing, right? Okay, how can you authenticate? There's really three main ways: Kerberos, certificates, and pre-shared keys. Pre-shared keys are the weakest form of authentication in this case, but that's what we're going to use in the example because it's simple enough. Okay, Kerberos is, if you've got a Windows domain environment, that's going to work pretty well. Otherwise, you got to set up Kerberos, which is kind of hairy, especially in a Linux environment. But in Windows, it just kind of works out of the box. Like they're pretty good with their support of that. And then there's always certificates, right, where you can verify each of the hosts using certs. Okay. Typically for VPN, like if you have someone coming into your organization, they're using a home machine or something like that, you're probably not going to set up certificates on the client side, right? And so usually it's Kerberos that gets used in a work environment. So Kerberos, I don't know how much you guys know about that. I know, like Sammy knows it better than I do, but I don't know if he talks about it in Active Directory or not very much. Does that come up? Oh, okay. Okay. What do you know about it? It's it's like a three-headed dog, right? That's okay. That's about what I know. No, nerds, not geeks. I don't know the difference. Okay, but yeah, Kerberos. This is the way that I kind of formulate it for people. It's like if you go to a club or a bar where you have to pay to get in, and they stamp your hand. Okay, so Kerberos, when you first come in, you have to go to a ticket granting center, which is going to authenticate you temporarily so that you can then go and get properly authenticate yourself. Then you get this token, and that's what I consider to be like the stamp on the hand. Once you have that token, that essentially gives you a session that you can work with, okay? And the session means that you don't have to re-authenticate for the duration of that session. So you can go to any particular resource on the network, and it'll just use that to identify you instead of you constantly providing username and password information, okay? So this works very well. It's quite a secure system. It's well understood. Windows implementation of it has a little bit of weakness in it. That's where pass the hash kind of can come from. But it is a very good system. So in an Active Directory environment, that's probably the way that you want to go. Okay. So once you have a system joined to the domain, then you have a good security foundation for IPsec to rely on. The problem is a lot of your users aren't using machines that are joined to your domain. So this is not always an option for us. Okay. Now, Kerberos can be used outside of AD, and some ISPs do it. There's Radius servers that will supply Kerberos. It does get a little hairy with Linux and stuff. Okay, so something to watch out for. It's probably not something you're going to end up doing. You're either going to do Windows Kerberos or none at all. Now, certificates, we're well familiar with that. I'm not going to keep making you use certificates. We're kind of moving on past that at this point. Okay, but you could see how certificates could come into this equally well. You know, the client gets a cert, server gets a cert, and then that's how they can authenticate each other and then set up their keys, etc. Pre-shared key is the simplest way, just like you know, your Wi-Fi router at home. That's the same basic idea. Okay. This is not the most robust approach because you have to agree on that pre-shared key and distribute it somehow. But in a controlled environment, this can work very well. Okay. So a downside, I don't know why, but in Microsoft, pre-shared keys are stored plain text on each computer. That doesn't seem like a necessary implementation, but that's the way that they've done it. Okay. So, you know, really, this is great for proof of concept, and that's what we're going to use it for, but that's about it. Okay. Okay, so security services. This is integrated with Windows Firewall, where you can specify services that the connecting system is allowed to connect into. You do that by setting up groups and then saying, applying policies to the groups. Okay. So let me just see. Do I want to go into that further? No, you'll be okay. I think you get the idea, basically. Essentially, like I've said, there's certain services you can specify. That's about as far as it goes, really. So if you do want to block people from accessing certain things, you can do that through security policies. We will do that a little bit in the exercise. Now, in terms of what gets protected, okay, so there's the source authentication. That's just identifying who's who, right? So certs are often used for that. The Kerberos can work just as well. Pre-shared key doesn't do a lot in that respect. You know, all you know is that somebody knows the key, right? So that's why it's the least favored of the three types of authentication. Data integrity, there's lots that goes into that, but basically there's a huge amount of hashing that goes on, okay? So the protocols that get used, like SHA-1, MD5, they're not the strongest in the world, but they're fast. And because this is traffic going by very quickly, it's not a lot of chance to fake things out, right? So even SHA-1 is not considered terribly secure. MD5 is crackable, but it still takes work, and you just don't have the time given how fast the transfers are. Okay. So they're still good to use, and they often are just because of that's about as speedy as we can get using hashes. So data integrity just makes sure that the packet that's being received hasn't been modified in transit, right? So that's where it trips over network address translation, because network address translation does rewrite aspects of the packet which get detected and trigger alerts, right? And so then the packet gets rejected for a lack of integrity. So a network packet that's sent through an IPsec protected connection includes that cryptographic hash of the packet. The hash is calculated by the sending computer. It gets encrypted and then included in the packet, and then that gets decrypted and compared to the end value. Okay, and if they match, then it's considered a good packet. Data confidentiality just means that when people are looking at the packets, they can't figure out exactly what's going on. Okay, there are some things that a listener, a witness could potentially, a malicious witness could potentially figure out, but they can't actually get the payload itself. Okay, so they may be able to identify the type of traffic that you're encrypting. It depends on the traffic itself. So because if you're enveloping IP packets within IP packets, sometimes you can give away extra information about what's in there. For example, VoIP packets. There's a quality of service that you have to specify to the routers so that when data is being passed through, it's being prioritized, right? And you can't hide that from the routers. If you can't hide it from the routers, you can't hide it from a malicious user who's trying to figure it out. So they may be able to figure out, oh, okay, I'm dealing with some voice over IP, for example. That doesn't tell them what's in it, though. It just tells them kind of the nature of the information. Okay, so Windows Server policies, by default, IPsec policies negotiate all of the authentication mechanisms and all the encryption techniques that each side can support, and then kind of like SSL, and then they agree on a subset that they're going to use. Okay. Now, Windows Firewall connection rules, they just basically authenticate whether you're allowed to connect to certain services. Okay, but we can combine these two to kind of add to our security, add extra layers. So IPsec policies, they define how a computer or a group of computers are going to communicate with each other. You can assign that to a single computer using group policy, local group policy, or to a group of computers using domain group policy. Okay, probably you'll want to go with domain group policy unless you're dealing with just a testing situation. And now you can have multiple policies, but you can only assign one to a computer at a time. So it's got to cover everything that you want to have covered in a single policy, okay, at least for each machine. So there are rules in IPsec policies that determine when and how an IP traffic should be protected. So you may be saying no one gets to touch this file server when you're VPNing in, right? And that would be one of your rules within the policy, okay? So you're going to have the filter list is by IP address, okay? And then the filter action is typically block or allow, right? So you define a source and a destination IP address range, computer name, port, and server type. Block, permit, or negotiate security. So negotiating security, here, it's really just what are we going to use when we're authenticating? What kind of encryption techniques are available to us that we can agree on, right? That it's pretty typical to leave that just as it is instead of to force a particular type of security in place. Just let the client and the server figure it out. Let's see. I'm going to skip that. Okay, here's an example of some policy rules. So, for example, I mean, no one uses Telnet anymore, but that might be a good reason to actually filter it significantly. So, filter number one, Telnet traffic from 192.168.3.32. So anything from that, negotiate security and force encryption. So that's why if you're using Telnet, basically they're saying, no. You have to actually have some kind of encryption. Let's go to SSH. Same thing with POP3. You could say you can have POP3 connections, but you actually have to have some kind of encryption in place. So if you don't have it, we're not allowing connections to POP3, okay? Now keep in mind, if you're using Telnet, normally that's a terrible idea because it's plain text, right? But if you're using IPsec, it's encrypted. So it doesn't really matter that it's not secure, okay? So here what we're saying is that from this particular source, you can negotiate security over telnet connection. And then policy number 2 says that any other telnet traffic is going to be blocked. So by having this rule, just like a firewall rule, on top, it's going to override this other one, right? They're not both going to be applied. So, okay, some predefined IPsec policies. There's on the client side, respond only. So it's going to negotiate and establish IPsec communications when requested. That is to say, the server is going to initiate the requirement. The server can request security, okay, or the server can require security. So it's either going to say, yeah, we're going to have a proper connection, or it's going to be like, well, if you can't provide adequate security, you know, I'll still authenticate myself for you, okay? If you go to require security, it's just going to close the connection if the client can actually authenticate itself. Okay, so like IPsec policies, security rules look at network traffic and then basically say yes or no about whether any kind of connection is going to be allowed. The connection capabilities are limited compared to IPsec policies. So generally, you know, you want to favor the first over the second. And connection security rules do not apply to types of traffic. They apply to all traffic between a source and a destination. So more of a broad stroke, right? And this is just integrated with Windows Firewall and Advanced Security. Okay, security associations. So I want to do that. I do want to cover authenticated headers, and so I want to do ESP. I'll just see. Okay. So another feature of IPsec, it's something that you can either enable or not. Is called authenticated headers. Okay, which basically verifies the data, the integrity of the entire packet. Okay, and now the problem with this is that because it's verifying things like IP addresses in the IP packet, it doesn't work well with network address translation. Okay, so digital signatures are used to verify whether anything's been changed, but you know, most of us out in the enterprise are using that at some level, and so this represents a little bit of a problem. Right? So the way that you can get around that is to encapsulate authenticated headers within another packet, and that packet can't be it can't be protected in the same way. Okay, and so that does compromise security a little bit. Let's see. I don't know if I want to do that. Yeah, okay. So authenticated headers carries an integrity check value. That's really what's checking the packet itself. And the hashing that's used, like I said, it's SHA-1, MD5. These are quick and dirty. They are a little bit weak, but given the speed with which packets are transferring, there's not a lot of a chance to actually compromise this in any way. Okay. Okay, so it's using hashing, which incorporates a secret that it can easily recompute. Okay, yeah, there's not that much more in there. Okay, AH and NAT, when the appropriate source and header IP address is changed, that forces a recalculation of the header checksum. So when you're doing network address translation, you're going to change those values. It's going to change the overall hash, and that's going to trigger an issue, right? There are other things in the packet header which are always changing. So if you look at things like time to live, that's always decrementing every time it goes through a router. They built that into the consideration, but they didn't build NAT into the consideration. So the fact that TTL decrements, that doesn't actually get calculated as part of the hash, okay? Because they knew that would be an issue. But when they built all of this, they didn't know that NAT was really going to be such an important part of our world, okay? And so they never really built that into, you know, saying the IP address should be kind of excluded from all of this. And again, it limits the utility if you're not checking the IP address. Okay. Okay. Yeah, so IP addresses are included in the integrity value check, and so modification causes problems, which triggers NAT difficulties, right? Same thing occurs with port address translation because the port values, if those are modified as well, that can become a problem. Okay. So what it essentially means is authentication headers, whether you're in tunnel or transport mode, is not compatible with NAT, which limits it to probably local area network environments or extended multiple LAN environments, you know. Okay, encapsulated security payload, on the other hand, this is a little bit more robust in terms of NAT. So here you're just wrapping that IP packet in an IP packet, right? And then you use symmetric encryption techniques, which are negotiated when the session is created. It doesn't encrypt the IP header or information for routing, okay? And that's necessary if we want it to work well with network address translation. So this is kind of the breakdown of how it works. You've got your original IP header, your TCP data, whatever that was, and then you're going to wrap it all. You're going to keep that original IP header, but you're going to wrap everything in a new ESP packet, essentially. So you're basically taking your old data and you're surrounding it with another envelope of information. Okay. Now that envelope is going to encrypt all of this, and so the only thing that's not encrypted is the original IP header and then that ESP header. That has to be transparent so that routing can work properly in a network network address translation environment. Now that's transport mode. In tunnel mode, here you're actually creating a completely new IP, right? And so the original IP header also gets encrypted along with all of the payload. Which one you do doesn't really matter, okay? This is probably the one that's going to work best. Well, they'll both work with NAT, actually. So, you know, it's really an implementation choice. I'm not going to cover that. Okay, so ESP includes header and trailer fields. So basically, you know, you're just covering that packet with another packet, which will be encrypted. And it does support tunnel and transport modes. Okay, so in terms of encryption, DES, not the strongest. Triple DES, that's pretty good. AES, that's much better. Okay, and Blowfish, these are commonly used to encrypt the packets. That's a symmetric cryptography, which, you know, amongst others, can be used. DES was actually cracked some time ago, so I wouldn't suggest that one. You can use null encryption if you just want to authenticate. You know, that just essentially means you're not encrypting. And the algorithm used for a particular connection, that's determined by the rules that you can set up to control negotiation if you want in a Windows environment. Okay. So you have to agree on an algorithm, but you also have to agree on the key that's going to be used, and there's a protocol for that. So I'm going to skip this part. I'm going to skip that part. I want to get to, oh, here we are. So to set up security associations, we use something called the Internet Key Exchange Protocol, so, or IKE, okay? So that just basically has the client and the server follow a predictable procedure to figure out what it is they can agree upon in terms of security mechanisms that they can apply together, right? So that includes security services, protection mechanisms, and any kind of key exchange that has to occur. An agreement on a key. Okay, now within IKE, there's two parts to the negotiation. There's the initial negotiation to allow them to actually talk securely. And then there's when they're, you know, after they've done that negotiation, they drop down into an actual session, and those could involve different information. Okay, so here they're just setting up a quick and dirty, kind of like, we want to talk quickly, we're going to settle on a key, but we want to do it in a secure way. Once they get that key, that's part of the process for quick mode, okay, where they're actually going to do ongoing encryption, with a more robust key. Okay, there's something very similar that occurs in SSL as well. Okay, so summary: IPsec is big. It's got a lot of features to it. If you're using the wrong ones in the wrong environment, things will break. We're going to do probably the simplest example of IPsec tunneling that you can do. Okay, so we're keeping it as, keep it simple, stupid kind of thing. We're not going to do any kind of Kerberos. I might do that sometime in the future, but I don't want to kill people. So the exercise that I want you to do, the assignment exercise, is this one, the layer 2 tunneling protocol on Windows. So it's Windows on Windows. Okay. It's big, but it's not hard. So I'll just kind of give you a quick summary down at the end of it here. Basically, you're going to have your general infrastructure, so your DC, right? You're going to set up a VPN server that has to have 2 NICs installed on it. Okay. One NIC is going to be on VMnet 8. One NIC is going to be on VMnet 4. The goal is to have a client, and I really want to emphasize this because people submit stuff that gives them no marks. You're not trying to set up a VPN within your local LAN. You want to set up a VPN from the outside that's able to get into your local LAN, right? So your client needs to be on VMnet 8, okay? And your VPN has to sit and straddle both networks, kind of like a router, but not really, okay? And then you establish a connection with your client to the VPN server, and that gives them access into the internal network. But I wanted this set up in a way so that most traffic goes to the outside world. The only traffic that actually travels through your organization is stuff that's intended for the IP addresses of that network. Okay. To me, like, I know here at NATE, when we were in the pandemic, students would be VPNing in. And if they were doing a Windows update would go through the VPN to download everything, right? And so not ideal, because VPN is not the fastest technology in the world. You're encrypting everything, you're putting a load on the server, or in this case, the VPN server. So I wanted to come up with a method where we were just setting it up so that most of your traffic is normal, and then anything that's going to the workplace gets routed differently. And so the images that I ask you to take at the end should demonstrate, first of all, that you have 2 adapters. One of them is going to be on VMnet 8. The other one's going to have a VMnet 4 IP address. Okay. The one that has the VMnet 4 IP address should be the point-to-point protocol adapter. Okay. That should have a 10 dot something IP. If those are reversed, you did it wrong. If they're both 192.168.202, you did it wrong. If they're both 10 dot something, you did it wrong, okay? And so you have to look at it. Now here, I'm doing a trace route to quadruple 8. The point of this is to show when I'm going out to the internet, I'm going through my normal default gateway, okay? So you can see that I've got my my hub at home, blah, blah, blah. That's all going through a proper process. When I trace route to an internal server, I can see myself going directly through the VPN to get there. And so I want to see that difference in your outputs, okay? So you only have to take 5 screenshots, and you can just do it right at the end, okay? So I want to see your Windows firewall, connection security, your main mode, your quick mode. Not that big a deal. The hard part is just going to be understanding what it should look like at the end, making sure that you're actually on another network, getting into the internal network, and then little details along the way, which you may just miss a checkbox here or there, and that can mess things up for you. Okay. But really, it's pretty paint by number. So if you have any problems or you're unsure about things, I can help people with that. Just kind of let me know. Yeah. Okay, any questions about that? You got a week to do it, so not too hairy. You're going to see the rest of this course is kind of more relaxed. So, all right. If there are no questions, I'm going to get a coffee, I think. It's coffee time for me. Yeah. Daddy needs a drink. Okay, I'll let you guys go.